Okay, let's give this assortment of review problem set a try. So a trumpet is sounded, it echoes sometime later. So let's draw the model of this. Here's a person playing a trumpet. They send out a sound wave. That sound wave goes shunk, 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 and it hits a surface, and it has to come back after that. This is the reflected wave. So the wave actually goes there and back in this sound. So we actually need a distance. We need a d, we have a time, and we've got a velocity. But the distance traveled, our goal is this distance. Our goal is, say, capital D. The distance the sound wave travels is actually 2d, so we can use distance equals velocity over velocity times time. And let's just say 2d equals 343 times 2.1. And we solve that, and we get d equals 360.15 meters. But we want to round that. Let's say our final answer is 360 meters. 2 sig figs. Because in the question we got 2 sig figs. Okay, the next question. These biology students playing some kind of low dubstep bass sound. What are the two shortest lengths of tube, closed at one end, that the physics student could play in front of the to hear resonance? Okay, so maybe we want to think about a standing wave in a tube. The very first harmonic, the shortest wave possible, would be a node antinode, and the next one would be the third one, node and then antinode. So there's our system, and our goal in the question is how long should this pipe be, and how long should this pipe be? Well, the velocity of sound is the same as before, 343. So we have the speed, and I can kind of write wavelength in terms of L here. For this top one, this length is 1/4 lambda, and this length is 3/4 lambda. I also know V equals lambda F, and I have the frequency, so I got V equals 343, and lambda is my goal. If I have lambda, I can then solve for my two lengths. Notice that if I have lambda, I can solve for my lengths. And the frequency was 105. So doing some math here, lambda works out to 3 sig figs, 3.27. That's meters. So wow, this is going to be a really long tube, biology student. That's just the lambda. So then there are two answers. We're going to plug lambda back into here. So length of tube 1 would be dividing, so I'm going to divide that by 4, 0.817. I can justify 3 sig figs. I got 3 sig figs here and 3 sig figs here. And length 2, it's going to be triple that. Notice L1 and L3. L1 is just times by 3, and we get L3. So triple that, we get 2.45 meters. So that's going to be a long tube. This tube, not too bad at all. Okay, so this question, we need to do an efficiency calculation. So we need to compare two energies, the energy we get out and the energy we get in. The energy we get out versus the energy we put in. Energy we get out is we've lifted a student a certain height. So we lifted the student a certain height. So that's going to be the energy, in this case, is the work done. It's the change of potential energy. So it's the change of potential energy. And the energy in, it's the electricity. It's the, I guess, yeah, energy electric. So this is going to be mg delta h. And the electricity is power times current. So that's our equation for energy from electricity. We won't use that in year 1 final exam, but it is an equation we'll have to be able to use eventually. So plug in our numbers here. 55, we'll use 9.8 as g. There's our height, and our powers, a lot of 7s times the time. Oops, power times time. Oh no, that's totally a equation we know. Never mind, I was wrong. So we get an efficiency of that number is 0.0897. So the efficiency, the final answer here, would be 8.9. Ooh, no, actually, no, never mind. 9.0. 9.0% efficient. Hey, one note about this equation here. This equation is totally doable for us. I'm sorry. So power is the rate of energy consumption. It's energy change or work over time. So then the energy released is the power times time. That's a completely fair equation we should be aware of. Okay, this guy, we got a dynamics problem. What's our first step here? That's right, it's an FBD. So we got a applied force, we have some friction, we've got gravity, and we've got a normal force. Notice the normal force is not equal to gravity because there's some component here and this component here, but this upward Fn component and this upward component of the applied force and Fn equal gravity. So after FBD, let's start with an Fnet equation. Because we're after the normal force, let's do Fnet in the y direction. Vertically, we've got Fn up plus the applied force times the opposite. We need the sine of 20. Let's just see why that is. Let's do a little triangle over here. There's a triangle. The hypotenuse is 75. This is 20. This is 90 degrees. We want to find this vertical side here and the sine of 20, SOHCAHTOA, opposite of our hypotenuse, y over 75. If I solve for y, I get 75 times sine 20. And the other force that's important here is gravity. We're going to say minus Fg. That's 0 equals our goal is Fn plus 75 sine 20. Take away m. Oops, not m. Let's do put in the number. 5 times 9.8. And we solve that, and we get Fn to be 23.3 newtons, but 2 sig fig, so it rounds to the answer that is on the sheet of 23. Okay, what is the speed of the block? 1 second. So we got to find, so our goal is, let's think about this as a kind of a bunch of steps. Our goal is VF. Where's it going to come from? It's going to come from acceleration. Where's that going to come from? It's going to come from an Fnet equation. Okay, so then now we can do Fnet in the x dimension, Fnet x. And look at our FBD. What are the forces in the x direction? Oh, there's an applied force. There's this guy right here. And there's a friction force. So let's do Fa cos 20. In this case, I want the adjacent side. I want this guy down here. It's the adjacent to 20. Minus the friction force. And that's where our normal force is going to be important. Normally, we probably wouldn't even ask A on a test. You'd have to figure out the normal force and use that to solve this guy down here. So MA, A is our goal, equals FA. The applied force is 75 cos 20. Minus the friction force, mu. And it's moving, so we need to use the mu K. It's the moving one, 5.2 times Fn. That's the number we just found. I'm going to use the non-rounded version. It'll help a little bit. I just want to point out, this guy here is mu Fn. I'm going to use this Fn in that calculation. Okay, so I put the mass that I had in there. The mass was 5. This guy was 5. And I find the acceleration. A equals 11.667 meters per second squared. Now, if I was asking for acceleration, I would round that. But my goal is actually VF, and I have a time. So VF equals VI plus AT. VF is my goal. VI is 0 plus acceleration at the 11.6 thing times the time of 1 second. Oh, nice, it's just 1. So it's the same number, so then VF equals probably just 12 meters per second. I can only justify, yes, 2 sig figs. Okay, so we got to look here at the slope of the graph and how the slope is changing. So A is just the slope. It's a position time graph, so all we care about for the velocity, oh no, wait a second, that's B. B is the slope. B is the velocity of the slope. Let's just talk as a slope negative or positive. So slope in 1 is negative, so this is going to be negative. Slope in 2 is 0. Slope in 3 is negative. Slope in 4 is positive. Slope in 5 is positive. Remember, we want the slope, not the value of the position, but the slope. So imagine a tangent line, negative slopes, 0 slope, negative slope, positive slope, and positive slope. So there's our column B. The velocity is the velocity increasing or decreasing. So for A, I need to think about the slope change. In 1, I go from big negative to small negative. Big negative to small negative, that's an increase. 2, speed is 0, and it's also constant. 3, it goes from a small negative to a big negative. So that's a decrease, small negative to big negative. Negative 1 to negative 3, that is a decrease. 4, small positive to big positive, that's an increase. And big positive to small positive, maybe let's say +3 to +1, that's a decrease. Finally, what's the speed doing? What's the speed doing here? Well, speed is the absolute value of the velocity. So although in 1, the velocity maybe is going from -3 to -1, that's the velocity. The speed goes from 3 to 1, so that's a decrease. Also constant, if the velocity is 0, the speed's also 0. The velocity in 3 was -1 to -3, that's a decreasing velocity, but the speed goes from 1 to 3, that's an increase. Here, the velocity was +1 to +3. That was a increasing velocity. It's also an increasing speed. Here, the velocity +3 to +1. That's also a decreasing speed. Notice the velocity change and the speed change, they sometimes match, they sometimes don't. So you can't make a rule for yourself. You got to reason through it every time. Remember, the speed is the absolute value of the velocity. Okay, last question. Let's draw some force diagrams. There's no friction. That's going to make things a little bit easier for us. This guy, only important force. Oh, there's friction. Oh, okay. This is friction over here. There's friction here. Friction force, tension force, and there's gravity and a normal force. Over here, we've got a gravity force and a tension force. These two aren't equal because the object accelerates. So now we got a system of equations. We can either do a system of equations or think of it as one big unit. I'm going to do the big system and flatten it out. So I'm going to flatten out that pink system, mass 1, mass 2. I'm going to make that pink system into this system, 1 and 2. What are the forces pulling the system kind of this way? Well, it's the gravity force on mass 2. And what are the forces pulling the system this way? That's the friction force. Now remember, the tension force is internal, so there are tension forces here, but they kind of cancel out. They're all within the system. So then there's our FBD, our Fnet equation then. Fnet equals Fg2 minus friction force, Ma of the system. This is mg of just mass 2. This is 1 and 2. And minus mu Fn. Okay, so we plug in the numbers. Really important point is to recognize that this mass is the mass of the system. It's the mass of this whole pink unit. The gravity force being caused by the mass 2 is only the mass of m2. So I've used the whole mass in the system's FNet. I've only used the 4 for mass 2. And we do that math, we sub everything in, and we get an acceleration of 5.65. And that rounds to the 5.7 meters per second squared. That's on the sheet. All right, that is this sheet finished. Great.